All right, good morning, everyone. So today we want to spend the morning with Galileo, a very interesting, a very interesting character. He was born here in Tuscany, actually in Pisa, but always considers himself a Florentine. As a young boy, his family did move to Florence, which is the capital of Tuscany, and he's always proud of the fact that he was a Florentine. He spent quite a bit of time in Padua, 18 years as professor of mathematics in Padua, which belonged to the Republic of Venice. At that time, Italy was not united, as you know, different various states. And so these are the two main areas in which Galileo worked in the Republic of Venice and in Tuscany, in Florence, the court of the Medici. I'm not going to spend a lot of time on his biography because I gave you so many resources. If you're interested to read his biography, he has a fascinating life, a very, very full life, full of controversy. He seems to have relished with that. But controversy was not just for the purpose of controversy. Once he became a committed Copernican, being a good Catholic, the way you can understand Galileo's motivation and his actions is he's trying to head off the church from embarrassing themselves in the intellectual world by insisting upon continuing to believe something, making it an article of faith, something which he knows is not true, that the earth is the center of the world and the sun and the planets go around the earth. He knows now that this is not true, and he's trying to convince the church that you don't have to hold on to this. This is not what's important. This is not the point of our faith and what we're about in earning our salvation. This is astronomy. And the Bible and our faith is not about astronomy. You need to be able to separate that. And of course, right now in these times, the church was not able to, and he was not successful, and therefore the trial and the condemnation and the house arrest and all the rest. And I think the film that I asked you to watch really depicts all that and goes through all that very, very well. And so I'm not going to really talk about those parts of this at all. We want to really move on, actually, to the next presentation of him as the physicist. But we do certainly want to hit the high points of his work as an astronomer. Because where are we? We're really looking at how this paradigm shift comes about. How do we go from what we call the classical Greek/Christian paradigm to the new paradigm, which basically is a Newtonian paradigm? How is that shift made? Well, we saw one way to do that is, first of all, just focusing on the cosmology. The rest of it all, the rest of the mental furniture follows eventually at some point. But just focusing on the science of it, on the cosmology of what the universe is like. We have the Ptolemaic system and we have the Copernican system. How do you move from the Ptolemaic system where the earth is stationary at the center of the world to being just one of the, as Copernicus says, just another mere planet going around the sun? How do you move from one sense which is so rooted in common sense and our own physical experience to something which seems at the time absurd? How is that done? Well, one way which is done is to start to discredit the Ptolemaic system, to show that what's some predictions that makes are wrong, begin to cast doubt on some of its fundamental assumptions by showing that these things, in fact, these held beliefs are in fact not true. And we've seen Tycho begin that by showing that the universe is not unchanging with the nova star, to show that the crystalline spheres can't exist because the comets move through the orbits of the planets, apparently crashing through the crystalline spheres, And finally, Tycho showing that the parallax of Mars is very much detectable, whereas the parallax of the sun is not, and therefore Mars, at least in opposition, is closer to us than the sun is. And that never happens in the Ptolemaic system. So at least on that one point alone, about just the actual configuration of the planets, Ptolemy must be wrong. So here's the process to begin to tear down Ptolemy's system. Well, that's not the only part of the story. Tearing these things down may work with the astronomers, but in terms of the fundamental belief that the Earth is stationary, no. It's going to take something much more than that. But certainly another component is to find supporting evidence for the new cosmology, for the one in which the Earth is at the center, and that the Earth is revolving around the sun like all the other planets. Can we find evidence for that? Copernicus had none. Copernicus had no new evidence at all. Okay, but here with the telescope, bringing in a new piece of technology, we will start to see real physical evidence that starts to support the new paradigm. And this is what Galileo does here with the telescope. So let us basically quickly move on to those discoveries. He actually is a professor for 21 years. First of all, 3 years in his hometown in Pisa, and then 18 years in Padua. By the way, Padua was a very well respected university still to this day in Europe, particularly on math and science. So being the chair of the math, having the chair of mathematics at Padua for 18 years was a very substantial and prestigious position, at least in Italy, if not and further around Europe. So by the time he gets to Padua and establishes himself, he is not a nobody in that sense. And this is where he does his great work on motion. This is where he does his experiments on motion, famous experiments with the pendulum and the inclined plane and all the rest. This is all done during his 18 years in Padua. But he gets sidetracked from publishing all of that work and pursuing that work with the telescope. He hears about the telescope. He sees the novelties on the street of what's being sold, and he goes ahead and makes his own telescope, a superior instrument that whatever could be found during that day. He learns how to grind his own lenses, experiments with different kinds of lenses and different thicknesses, and comes up with a quite usable telescope. And the first thing he points it to is, if I gave you a telescope and you had never looked at it before, the first thing you would look at in the sky would be the moon. And if you've ever had the opportunity to look through a telescope, no matter how many years back it would be, if you ever look through a telescope, I hope everyone has had that chance at some point, and the first time you see the moon, it is very impressive. It is startling. It's something that you remember when you see the moon that close. And here is one of his telescopes. This is in the Science Museum in Florence. This is their pride and joy. This is the center of their collection. When I was there, it's in a beautiful glass case in the middle of one of their most important rooms. And this is one of his later more powerful 30-power degree telescopes. This all happens in 1609, a very important year. That's the same year that Kepler publishes his new astronomy. So 1609 is the year that we have the telescope discoveries from Galileo, and we have the new calculating device from Kepler, at least the beginning of the new calculating device. Those more accurate tables won't come along for another 10 or 15 years, but we have the makings of a new model, a more sophisticated model, one moving away from the circles of Copernicus to the ellipses and the three planetary laws of Kepler. So we have a better calculating device. But again, that's not going to do it either, because the calculating device is only of interest to the astronomers and the astrologers. Again, you're not going to convince people with a better calculating device that the Earth is not moving. That's going to take something else. That's not going to be done with astronomical theories or with astronomical discoveries. You're not going to convince the guy on the street. You're not going to convince the theologians and the philosophers who have a vested interest in this paradigm that the Earth is moving. It's going to take something else for that to happen. But the telescope, the discoveries of Galileo. He publishes the Starry Messenger in 1609, and this is what he talks about. This book becomes a sensation, and overnight Galileo becomes the most famous scientist in Europe. First of all, he says, wherever you look in the telescope, you see so many more stars through the telescope than you see in the naked eye. Now, why would that be? For example, the Milky Way. When you look at the Milky Way, finally you can see that what it actually is not this cloudy, milky cloud, which is all that could be seen until this time, but it's actually a very, very dense configuration of stars. The stars are so dense in that area that it looks to the naked eye like a cloud, but in fact, it is a very, very high concentration of stars. And no matter where you look, you see more stars through my telescope than you do in the naked eye. What does that suggest to him? It suggests that the stars are, never mind of different brightnesses, that's possible, but certainly there are different distances away. And that's just exactly what Copernicus was trying to put forth, that we don't really have a firmament. We don't have this dome over our head, which is what was understood for 5,000 years of civilization. That's in fact not what you see. That's not actually not what we have above our heads. What we have is these stars of different distances away. And how far away are they? How extensive do these stars go? Further and further away. Because here with my telescope, I can see things so much dimmer. Presumably with a more powerful telescope, I could see things even dimmer than with my telescope. And wouldn't they be even further away? Where does this boundary come? So here we are again, destroying the paradigm of the enclosed universe, which is surrounded, its boundary is the stars, the fixed stars, and beyond that, we have heaven and God. He looks at the moon, and the moon is not perfect. It's not made of ether. He says the moon, if anything, looks more like the earth than anything else. It has mountains. It seems to have seas, which we still call them, the Mara, the dark areas where the Apollo landings go, the Sea of Tranquility. They're still called that from Galileo, thinking of them as bodies of water because they were darker. There's mountains and valleys and protuberance. He even measures the shadows of the mountains on the moon and gets an estimate of how tall they are. Yeah, typical modern scientist. He's there measuring things. And he even has the notion that the moon, when it's when the moon is in its phases and most of it is dark, you can still see it quite nicely through the telescope. Of course, you can see the dark moon when it's in a phase, half moon, quarter moon. If you just let your eye focus on the moon with a nice sky, you can see the rest of the disk very, very easily. But with the telescope, he could actually see, the ghostly dark part of the moon. It was lit quite enough that the telescope could see some of its major areas and major configurations. And he realized what was happening where that light was coming from. It was not coming from the sun, because the whole half of the moon was lit, but it was turned away from us except for the phase that was truly lit by the sun. What he realized is it was the earth, that the sunlight from the earth hitting the earth and reflecting back up onto the moon. And what he was seeing was earth shine on the dark part of the moon that you could actually notice through the telescope. And he saves the best for last in the Starry Messenger, which is discovery of the 4 moons of Jupiter. And this was an incredible sensation. This was totally unexpected, that there are in fact 4 bodies circling Jupiter. And this is the famous picture from his book to show his observations from each night. You can see this is in December 7th, 8th, 10th, 11th. And first of all, he sees 3 little stars around Jupiter. Then he sees them again the next night, but they're in different places. And then all of a sudden there's only 2, and then 2 again, but and then the 3, and then finally there's 4. And what he realizes is he's looking at moons going around Jupiter. Well, the paradigm tells us that the only center of motion in the universe is the Earth. Everything goes around the Earth. The Earth is the center of all motion. No, these 4 moons have their center of motion, Jupiter. Jupiter is their center of motion. And what about the objection that, well, if the Earth is moving, what a silly idea, how can the moon keep up with the Earth? Right? We know everyone has always agreed that the moon is going around the Earth. Well, it's no problem if the Earth is stationary. If the Earth is moving, how does the moon keep up with the moving Earth as it goes around the sun? Galileo can say, I don't know, but these 4 moons of Jupiter have no trouble. You've agreed that Jupiter is either moving around the Earth or it's moving around the sun, but Jupiter is certainly going around the sky every 11 years. And these 4 moons have no trouble keeping up with the moving Jupiter. So much for that objection that the Earth couldn't be moving because our moon could not keep up with it. No, clearly that is not true. So these are the 4. These are the great discoveries, the first discoveries from the telescope, which he publishes. And again, it is a sensation. And here are just pages from it. Here's the idea. Here are the stars that you can see with the naked eye. And here he's drawing the stars that he can see with the telescope. Funny story, the 4 moons of Jupiter, he calls them the Medicean stars for the house of Medici. He wants to leave Padua. He's tired of teaching. He wants to go back home. Padua, of course, is part of the Republic of Venice. He wants to go back home to Tuscany, to Florence. And so in the telescopes that he makes, the very most beautiful telescope that he makes, he gives a gift to the court of Medici, to the Duke. And he names the 4 stars after the Duke and his 3 brothers, also the Medicean stars. Well, the Sharmas are not going to go for that. So Kepler gives them a different name, as it turns out. He goes into mythology and looks at the companions of Jupiter and comes up with 4 famous stories of Jupiter either seducing somebody or tricking somebody or whatever, figures that are prominent in the stories of Zeus. And he comes up with the 4 names of Io, Europa, Ganymede, and Callisto. And those are, in fact, the names that stick. And so we can thank Kepler for the 4 largest moons of Jupiter. Jupiter, of course, I think now has, I don't know, it's up to 28 or 32 moons now that we can see with the modern telescope. I'm not going to read too much from the text here. You can read the text yourself, but this I would like to read and comment on. When Galileo discovered the satellites of Jupiter, a Florentine astronomer published this objection. There are 7 windows given to animals through which the air is admitted to the tabernacle of the body, to enlighten, to warm, and to nourish. Those are the purposes, that is, the uses that we have to enlighten, to warm, and to nourish. What are these parts of the microcosm? That is, what are the parts of the body which reflect in the same equivalent parts to the universe? What are those parts to the microcosm in our body? 2 nostrils, 2 eyes, 2 ears, and a mouth. That's the purpose of the nostrils, the eyes, the ears, and the mouth. They are The reason why we have them, the reason why they're there is to enlighten, to warm, and to nourish. Everything must have a purpose. And if you want to understand why things are the way they are, you look for their purpose. That's the heart of this paradigm. So in the heavens, as in the macrocosm, that is the heavens, their configuration mirrors our configuration in the microcosm. Our body and the universe are one by the same creator. There are two favorable stars, two unpropitious, two luminaries, and Mercury undecided and indifferent. Clearly, the two luminaries would be the sun and the moon. Yeah, at the time, the sun and the moon were planets. There were 7 planets. The 5 historical planets of Mercury, Mars, Venus, Saturn, and the sun and the moon make 7. For this and for many other similarities in nature, such as the 7 metals, etc., which would be too tedious to enumerate, we gather that the number of planets is necessarily 7 because of this reflection of the fact that the macrocosm and the microcosm have to be in harmony. And since we have 2 nostrils, 2 eyes, 2 ears, and a mouth, therefore, there must be 7 planets. This is not a joke. This is arguing from deep inside the paradigm that there is a parallelism between the microcosm and the macrocosm of the universe. We being the microcosm, the human being the most important object in the physical universe. And our construction is reflected in the construction of the universe. That's how God makes the universe. Moreover, these satellites as Jupiter are invisible to the naked eye and therefore would be useless. Therefore, they do not exist. Because we can't see them, what use would they have? Clearly, there's no use in astrology for them. We can't see them. Matter of fact, if we can't see them, what use do they have at all? Well, without a use, without a purpose, they simply don't exist. That somehow or other, these lenses are playing tricks on our eyes. And this was a very deeply held belief for a long time. People who wanted to reject the discoveries of Galileo simply said that these things are just tricks of the glass, which of course, is well known as creating tricks with glass and lenses and things like that are quite doable and quite knowable at that time. Besides, the Jews and other ancient nations, as well as modern Europeans, have adopted the division of the week into 7 days and have named them after the 7 planets. Now, if we increase the number of planets, this whole beautiful system falls to the ground. You can't be destroying what clearly we have built here that clearly makes sense, that clearly is true by disrupting this whole, by introducing things like this. This cannot be so. These moons cannot be so for these reasons. These are very, very serious reasons inside the paradigm. So it's a wonderful view if we've forgotten, the fact that we're focusing just on the astronomy part, just trying to tear down poor Ptolemy and supporting the sunset system. There's much more at stake here than just what calculating device you're going to use and what you're comfortable with. There's much more at stake here. And I think this really shows it very well. And finally, a couple of years later, he makes 2 more very important observations. One is the phases of Venus, which very much like Tycho's discovery really pretty much knocks out Ptolemy's system. Here's Ptolemy's system, the geometric system, where the Venus is always between the sun and the earth. Venus is always closer to us than the sun. And here is the sun-centered system where we are going around the sun and Venus is always inside our orbit. Here, the Venus is always backlit. Here, sometimes, in fact, it is fully lit. And as Venus goes around the sun, as we observe it, it will have phases just like the moon, if in fact the Copernican idea is correct. And here is Galileo's observations of Venus. Okay. Here are the phases of Venus. Notice that as Venus gets more and more lit, as it goes behind it, it will get smaller in the telescope. And here they are smaller when they're more lit, and in the crescent phases, they are larger in his telescope. This is a complete confirmation of this picture and a complete repudiation of this picture. And this pretty much destroys the Ptolemaic system for the astronomers. And the astronomers now begin to move to Tycho's system. Tycho's system supports all of this, except the Earth is still stationary. That's what's real. That's what must be preserved above all else, because everyone knows that the Earth is stationary. Anything else is just a silly idea. How do we marry this picture that we can see, this observation that we see with the telescope, with the fact that the Earth must be stationary? You go to Tycho's system, okay, which allows Venus to go around the sun and for us to be observing it from a central platform, and we would see this just as well as we would in the Copernican system. In fact, the Tycho system is mathematically equivalent to Copernicus' system. So very much the church astronomers were many. There were many important astronomers, the Jesuits. There was a big observatory in Rome, in the college in Rome. One of its major departments was in astronomy, very serious astronomers. Those astronomers exist still to this day. The Vatican still has telescopes around the world, and some of the big mountain tops around the world, they still maintain some telescopes. The Vatican is always interested and always supported astronomy. Those astronomers begin to move to Tycho's system. And the last discovery at that same time, coming out at the same time, is the sunspots. Okay, here is the most pristine of all of the objects of the ether. If anything should be perfect, it would be the sun, and it is not. Okay, the sun has these dark spots. Big controversy. Brother Schneider says that no, they're really kind of like clouds above the sun, or maybe they're even satellites that are going around the sun and they're just blocking the sun. And Galileo shows that no, these are actually spots that are truly on the sun, because he shows in this photo essay how the spots move continuously across the face of the sun. And the only way to explain that is, in fact, that the sun is rotating, that these spots are on the sun, and the sun itself is rotating just the way we know the moon is rotating, and just as Copernicus is telling us that the Earth is rotating. Here, the sun is rotating as well, with these dark blemishes on it. So just as the moon is more Earth-like, the sun at least is not this pristine thing, which is, no. The spots show that, and the rotation. And so these are the great discoveries of the telescope. Make no mistake, guys, if Galileo hadn't made these discoveries, someone else would have made them a few years later, if even shorter. Once Galileo published the Starry Messenger, this was a great sensation. Every astronomer in Europe wanted to get their hands on a telescope, wanted to begin making telescopes, and people began doing that. Okay, so these are not the discoveries of Galileo which are unique to Galileo, that only Galileo could have made. Okay, other people came along, and again, there was priority disputes as to who saw what first. Okay, very, very soon after. They're important. Galileo was an incredible observer. He was able to understand what he was seeing with these very primitive telescopes. It's amazing when astronomers now look through his telescope today, a modern version of it, to see what he saw. It is amazing how he was able to interpret correctly what he was looking at. And to draw these pictures that he drew. But this is not something that would not have been done just soon after by someone else. Okay, as important as discoveries are from him. Okay, let me stop here because that's basically mostly what I want to say about this presentation. Any questions about these discoveries by this new technology of the telescope?
I have a question, Peter. I'm wondering if you know what level of magnification they were able to achieve back then with those new telescopes.
Yes, yes. In fact, he created a telescope with a magnitude of 30. 30 magnifications was his best telescope, which was pretty good. Pretty good. By the way, one other thing in looking at this telescope, the planets in the telescope were disks. They were small little disks, like we saw those pictures of Venus. Okay, the stars, not at all. The stars continue to be just a point of light, and he points this out. He says, although I can see the disks of all the planets right up through Saturn, though Saturn's got these funny ears. He couldn't figure out what the ears were on either side of Saturn, and then they disappeared as he kept watching. As the months went on, the ears all of a sudden disappeared, and then it was just a clean disk, and then the ears began to appear again. His telescope just could not resolve the rings of Saturn. It was just a fuzzy glow on either side. And sometimes as Saturn continues to revolve, it also, moves the way the Earth does in terms of pitching back and forth. And sometimes the rings of Saturn disappear. We look at them right head on. We see them right in the plane of the rings, and you can't see them even with the telescope. They kind of disappear. So he couldn't make out what was going on with Saturn at all. It was only the next generation of more powerful telescopes that could resolve the rings of Saturn. That was done by Huygens. But anyway, all the planets were disks, but the stars continued to be just points of light. And he said, what does that tell us? That tells us that the stars are much, much further away than the planets, just as Copernicus tells us. That the stars are very far away because they have a fundamentally, I can't resolve them. Not even a bright star like Sirius. I can't resolve, whereas I can resolve virtually all the planets, even the hazy Saturn with its ears. So there is a fundamental difference in distance between the stars and the planets. It is not this, picture of Ptolemy where the fixed stars are right behind Saturn in that last big orbit. No, that's not true. The telescope shows that is not the case. So you see where just Ptolemy's system is just pretty much dismantled with this new technology of the telescope.
Peter?
Yes.
Peter, he understood that the stars were further away than the planets, but did he understand that some stars, was he saying that, did he understand that the dimmer stars were further away than the brighter stars?
Yes, that's what he assumed. Yes, that would be the natural assumption. If distance is correlated with brightness, which is true for lights, and these are lights, so that would be the natural assumption.
Well, but was that his assumption?
That was his assumption.
That was his assumption. Okay.
Yes, absolutely. That this was evidence that the stars were not on a fixed firmament, that the fixed stars were not on this largest, most exterior globe. Not at all. They were free in space. And in fact, this already began speculating before the telescope, right? We saw that with the early speculations right after, in the very next generation after Ptolemy. I'm sorry, after Copernicus, that we had Digges, the British astronomer, proposing that the stars were of varying different distances, of unending distance, of indiscriminate, not knowing how far away these stars would be. They were sprinkled throughout the universe. This was already a speculation. Here we have the telescope supporting, not proving, but supporting that speculation. And so, yes.
I watched a part of your very nice lecture on Kepler and Galileo on YouTube last night.
Oh, thank you. Yes.
I want to get back to Kepler a little bit because Galileo was a chair of, had the professorship of mathematics, and he was a great mathematician. So when the Starry Messenger, in terms of a timeline of Kepler publishing his first and second laws, had you talked in that lecture about Galileo's 2 letters over a lifetime to Kepler, but he congratulates him and embraces him as a fellow Copernican. But did Galileo understand the mathematics, the genius of Kepler, and the accomplishment of the mathematics? Did Galileo get that?
Thank you for that. That is an excellent question, and you anticipate one of the major points I'll be making a bit later on. But let me go ahead and do it now to an answer of your very, very excellent question. So the historians of science do believe that Galileo did understand Kepler's work. He was a good enough mathematician to understand what Kepler was about and realizing the laws, the ellipses and stuff. But he was very skeptical of Kepler with the mysticism and all the craziness surrounding, just the math, was just so crazy with Kepler that he was skeptical. And it was hard for him to move away from the circles. It was very hard for Galileo, as the great scientist that he was, to move away from those circles, because the circles just seemed to make sense, and the ellipse, didn't. It was very hard for him. But they do believe, the astronomers, historians do believe, that Galileo understood what Kepler was about, but was skeptical of it. And what Galileo was about, as we'll see, was he was trying to have people understand that the Earth could be moving and we'd not realize it. That's why it makes sense that the Earth is moving, that it's not just simply this common sense that the Earth is stationary. I want to explain why the Earth can be moving and we not realize it. And that was his major thrust. That's what he was trying to convince the world of, to move away from this stationary Earth. And so Kepler's discoveries of the ellipse as opposed to the circle, and the area law, and the crazy, almost numerology law of the t squared over the a cubed, Galileo really didn't know what to make of all of that. And in fairness, a lot of astronomers didn't know what really to make of all of that.
I can believe
Area
that.
law was hard to use. It was much easier to use the circles to compute where the planets would be in the sky. Kepler's work was difficult to absorb.
I'll bet.
Yeah. Okay. So
Nobody really understood Kepler.
Until Newton came along. People loved his tables, and his tables actually did win out. They were clearly more accurate, and both the astronomers and the astrologers were happy to use his tables. But they didn't know what to make of his 3 planetary laws. First of all, they were independent of each other. There was the ellipse, okay. Well, then there's this area law, which has nothing to do, that could have been an oval, could have been an egg shape. Still, the area law could have been true or not, had nothing to do particularly with an ellipse. Then there's the third law, which is totally out of left field, which has nothing to do with anything. So the laws are totally independent of each other. People didn't know what to make of Kepler's work until Newton.
Thank you.
Here, we cannot leave Galileo without reading the most famous quote. One of the ironies is that this comes from a letter called the Assayer, in which he's in another fight with another Jesuit, this time about comets. The Jesuit here is right, saying that the comets are in fact up in the sky, just the way Tycho had shown. They're way up in the stars, way beyond beyond the moon, etc. And Galileo said, "Well, I'm not so sure. Maybe not, but we need to have more evidence. Maybe it's a." He's just seems to be disagreeing with the Jesuit just for the sake of disagreeing with them. So it is ironic that where this famous quote is actually in a document of his where he is absolutely dead wrong scientifically about what he's trying to disagree with the Jesuit astronomer about the nature of comets. One thing he truly gets wrong, that he doesn't want to go all the way, that the comets are way out there in among the planets going around the sun. But he says philosophy is written in the grand book, science. I mean, the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It's written in the language of mathematics, and the characters are triangles, circles, and other geometric figures. That's the mathematics of Galileo. That's the mathematics that he was trained in. That's the mathematics of the Greeks. Now we would say functions and equations and differential equations, but the idea is the language of mathematics, without which it's humanly impossible to understand a single word of it. Without it, one wanders through the lab around in a dark labyrinth. So this is exactly, where mathematics stands today. Mathematics is at the heart of all scientific description. And it's a very beautiful expression of this idea. And if this is not one of the most famous, if this is not the most famous quote in science, it's certainly in the top three. On being Babylonians, you have to read yourself. His wit is just very biting. There's again another Jesuit. I don't know if one's making a claim about swirling eggs around in a sling and you can make them get boiled, and Galileo is just ripping him apart, making fun of him. You just have to read it. It's very funny. And so we come to the dialogue in which he's going to put forth his fair debate between the Ptolemaic and the Copernican system. And here's a picture. Here's the front piece. Here's a picture. Here he has his moons of Jupiter. He's showing his great discovery. The sun is in the center. Here we have the moon going around the earth. And we have Jupiter out here with the 4 moons. And we have the picture, of course, of describing the retrograde motion from the Ptolemaic system. Notice everything here is circles for Galileo. Galileo is not particularly interested whether it's an ellipse or a circle. This is not the point. The point he's going to try to make here in the dialogue, he's going to go through all of his discoveries, et cetera, that were made back in 1610 and 1613. Here, the book is published in 1632. He's going to go through it all, but the point is he wants to show that the Earth can be moving around the sun. It is not an absurd idea. What we see around us, what we experience, is not a proof that the Earth is stationary. It is not a proof of anything at all. That what we experience here about how we experience ourselves here on Earth would not change if the Earth was spinning on its axis once a day and going around the sun once a year. Everything would be exactly as it is now, because in fact, the Earth is doing those two things. It is not necessarily the case that therefore the Earth must be stationary. That's the purpose of the dialogue, is to show that to be the case. And he does that with the law of inertia. So he makes his argument, the first one being the law of inertia, that there's no proof that the Earth, in fact, is stationary. He goes through all of his discoveries of the telescope, tearing down, Ptolemy building up, supporting Copernicus. And finally, he has his pet theory of the tides, completely wrong. He believes that the motion of the oceans or the tides demonstrates that the Earth is moving. Not true, right? The tides are caused by the gravitational attraction of the moon and to a lesser degree the sun. It has nothing to do with the moving Earth. So here we have, again, Galileo getting something dead wrong. Okay. And he ignores the Tycho system because it's not the point. He wants to show that the Earth, that the sun, that the Earth is moving and not stationary. And so Tycho system, Ptolemy system makes no difference to him. He wants to show that this is not the case, that the Earth is moving. And so there's no point discussing something which is completely mathematically equivalent to Copernicus, except it holds the Earth stationary. No point in discussing such a system. That's not what he's about. And we go through, getting in trouble with the Inquisition, being the trial and the whole thing, being condemned under house arrest as a very old man. This is an interesting slide, I think. Although he is condemned to house arrest. He's not able to publish anything more. All of his works are put on the index. Everything that he ever wrote is put on the index just for good measure. It's a funny story at the trial. he does say, eventually when he realizes the jig is up and he's not going to win this one, he said, well, maybe I did go a bit too far in supporting the Copernican system. Maybe I wasn't really as fair as I should have been with the Ptolemaic system. I can fix that in my next book. No, Galileo, there's not going to be a next. You're not writing anything ever again. You're done. We are shutting you down. There is no next book. But given that what the church tried to do, this is a very interesting slide. That in fact, they did shut him down in Italy, where the power of the church was most importantly. But outside of Italy, Galileo, again, was the most famous scientist in the world, okay, in Europe, from the Starry Messenger on. And so his works were, very much alive, translated, et cetera, even though the church tried to shut him down. He even was given an award by the Netherlands for his solution to the longitude problem. Basically the longitude problem is what is your longitude? Your latitude is relatively easy to measure. It's either the height of the North Star or the height of the sun at noon will tell you your latitude. But for longitude, you need a clock. You need to know what time it is where you are in the middle of the ocean compared to, let's say, Greenwich, some arbitrary fixed place where they call it zero. You need to have a clock. And Galileo had the idea of using the moons of Jupiter. Since everyone could see the moons of Jupiter, if we could have accurate tables of exactly where the 4 moons of Jupiter when, you go ahead, look in the sky, see where the moons of Jupiter are, and know what time it was. And you can compare, therefore, your time to Greenwich time, and you would know your latitude. This was a very, very big, your longitude. Very, very big problem. The problem, the nautical problem of the age was not solved until the late 1700s. Finally, a clock was designed that could be taken out in the ocean and still be accurate. And so all of the European countries, in fact, all the countries of the world, any scientific country was interested in trying to solve the longitude problem. And Galileo, there he is, blind under house arrest, not be able to see anybody, is putting forth a solution to this problem. And the last thing he does a year before he dies is he's working on the design of a pendulum clock, going back to one of his earliest studies, the study of the pendulum. So just a remarkable man.
Peter?
Yes.
I don't know if you've seen it, but I just a couple of months ago read a very interesting book, and the title was Longitude, about the genius English clockmaker that finally managed to do it, and it describes that story. I forget the guy's name, but it's a wonderful story. I forget the author of the book, but it's called Longitude.
Dana Sobel. The clockmaker is Harrison, and the author is Dana Sobel, who is the same author of Galileo's daughter.
Right.
Same historian.
Yeah.
Wonderful book. Highly recommended. Thank you for that.
It's a great story.
Longitude. Matter of fact, I highly, highly recommend Galileo's daughter. What a beautiful biography of Galileo's, shown through these letters from his oldest daughter. So that is Dana Sobel.
Did I hear on one of your lectures that, or somewhere in the last couple of weeks, that Kepler had a theory about the tides that was better, more conforming to what the truth about the moon?
Yes, Kepler understood it was the effect of the moon. And this was not completely unknown. Mariners, could see this, that the moon, given its different phases, et cetera, kind of there was a regularity of the tides with the moon. This was not completely, a crazy idea. But Kepler is the one who made more of a systematic study and did convince himself that it was the motion of the moon, and when the moon was close and far, et cetera, that would affect the tides. Galileo was totally aghast at this. He said, Kepler, I thought we were on the same side here. I thought we were on the same team. We're trying to get rid of all these occult forces and all these craziness. You're talking about the moon so far away affecting the water here. How could that possibly be so? So again, Galileo being dead wrong. So all of us are products of our time.
Except Kepler.
Okay, Kepler was your hero.
Yeah.
Now, as a matter of fact, we can point to Kepler in terms of when he was looking for the forces that would move the planets around the sun. He came up with this magnetic force. Fair enough. He found himself a force, but the force had to push the planets around. The forces were kind of like a broom, pushing the back of the planets, pushing it around, sweeping it around with this magnetic force. Okay, and that is right out of Aristotle, the idea that it takes a force to make something move, whereas in fact, the force of gravity pulls the planets directly in, straight in is what causes the planets to move in those closed circles. So Kepler got that wrong. He was still in the Aristotelian paradigm of forces in motion. Okay, so I encourage you, if you haven't had a chance to take a look at these slides, they're very self-explanatory. They have a lot of good information in them about Galileo and his life and his legacy. And, if you have the time to read them, I think you will find them interesting. But we want to move on to the last stage of breaking down the old paradigm and beginning to convince people. And again, where do you begin convincing people? You convince people, the experts, you convince the scientists first of the new science. And then little by little, it becomes accepted into the wider culture. The educated layman, the man on the street, educated layman, that kind of, and finally, gets bleeded into the general culture. It's a very, very slow and long process. The process starts with Galileo. Galileo is going to explain not only why the Earth can be moving and we not notice it, but that there's much more to understand about the whole notion of motion. And his approach to motion, how he studies motion, is truly revolutionary. He, in a sense, really invents the way modern science is done. And that's what I hope to show you in this presentation. We won't complete it today. We'll complete it next time. But let's get started with this presentation of how Galileo basically invents modern science, the methodology of modern science, bringing mathematics into the study of nature directly. They say, yeah, but didn't Ptolemy and Copernicus and Kepler bring mathematics into the study of nature? In a sense, but that's, in a sense, pure math. They had these lights in the sky and they were just building geometric models that would reflect what the lights would look like. It was a planetarium system. Very impressive piece of work to build mathematical models that can produce what we see. But there's no analysis of why these are what they are. The models do not explain really anything. They only describe. Why do the planets move the way they do? Why do they move in ellipses? Why do they change their speeds? What keeps them up in the first place without the crystalline spheres turning around? What is the physics behind all of this? Ptolemy, Copernicus, and Kepler had no real answers. Kepler tried to begin to answer those questions. To his credit, he said, we're not going to be done until we can answer that other half of the questions, but he was not successful at all in discovering what those reasons were. Galileo actually doesn't address those questions. He was not interested in actually the forces about the stars and the heavens. He was happy with the circles. He was happy with this kind of, they move with this kind of circular inertia. He was not going with the Aristotelian system of the natural motion of the ether moving in circles, but circles were a natural motion for sure. And once you had a body spinning, it would continue to spin. So that's why the Earth was spinning. And that is true. There is something called, angular inertia, rotational inertia. But things do not move around the sun. Things do not move in a circle without some kind of a force. Galileo was happy to believe that, well, no, the Earth and the planets would move around the sun because that was a natural circular motion. There was kind of an inertia. Once you set something moving in a large circle, it kind of would continue moving in a circle. He still was married to this idea of circular motion being fundamental. It's wrong. Galileo, again, was wrong. But what he did study, what we are going to look at now, is his investigation of terrestrial motion. And this is where he lays down the beginning of modern physics. We can't call it modern physics, we'll call it classical physics, right? The physics of Newton, the physics of the 19th century. It begins here with Galileo. And one of the things that he does in all these investigations is, in fact, he does show that the Earth can very well be spinning once a day and going around the sun once a year, and we would not notice it. Okay? And that's just part of what we want to see in this presentation. And it's all wrapped up in his final work of 1638 that he got published under house arrest. It got published in Netherlands. The church kind of looked the other way. No one said, let's beat him up or let's torture him or let's put him in a dungeon, because they just made believe it didn't exist. It wasn't about the stars. It wasn't about the planets. It was about this very technical thing, mathematical book. It looked like Euclid's Elements when you page through the discourse. It looks like a book of geometry. So the church just gave up. But it was not published in Italy. Could not get anything published in Italy, but it was published in the Netherlands. It was snuck out by a friend and sent to the publishers up in the Netherlands. Very quick review of these slides, right? Aristotle's theory of terrestrial motion and the ether motion. The natural motions of Earth and water being heavy, naturally straight down to the center of the universe, which would be the Earth. Air and fire moving straight up because of their natural lightness. The ether naturally moving in circles. Violent motion requires an agent, requires a force. If there is no force, there is no violent motion. Once the force stops, the violent motion will stop and natural motion will ensue. It can only be created by a contact directly from one body pushing on another. That's the only way that you get violent motion. That, of course, was criticized because what happens when you shoot an arrow after it leaves the bow? Why does it continue to move? Clearly, it's a violent motion. It's moving in some kind of an arc. It's not moving straight up or straight down. The arrow clearly is made mostly of earth. Why is it moving straight down right away? Why does it continue to move? And the people in the Middle Ages developed this idea of impetus, that the bow somehow or other gave a quality to the arrow called impetus, which was able to continue to move until the air resistance kind of drained the impetus away. And once the impetus was all gone, the arrow would then fall straight down to the earth with its natural motion. The impetus was related to the speed. The greater the speed something had, the more impetus it has. And as it lost speed, it lost impetus until it finally went to just natural motion and began to fall straight down with its own increasing speed, but that's natural. There's no force involved in that. It's just sinking its natural home, which is the center of the universe, which is the center of the earth, and that's why the arrow falls straight down. So this is Aristotle's theory of motion. It's been called the theory of common sense. It makes a lot of sense. You can demonstrate with many, many examples and experiments why these things are true. You can push a book along a table and it will stop moving as soon as you stop pushing it, et cetera, et cetera. The impetus theory helps a bit. You can give the book a good push and it'll slide along for a while until it finally stops on the table. Okay, so this physics is not completely silly. It lasted for almost 2,000 years, but Galileo was going to overturn all these ideas, as we'll see. Again, the review of tearing down the old paradigm, Tycho's discoveries, Galileo's discoveries of the telescope. The advances to support Copernicus' system. Now on the positive side, we have all of Kepler's work, okay, showing this incredibly accurate new calculating device using the stationary Earth, using the fact that the Earth and the planets are going around the sun according to these three laws. The tables, the accurate tables that are able to produce using this model is unprecedented in history. Clearly, there's something to this. A great support of the stationary Earth, basically the Copernican paradigm, and Galileo's discoveries of the telescope, again, supporting the Copernican system, particularly the phases of Venus being perhaps the most important. Okay, so what is the objections to the moving Earth? Okay, why is it so difficult to move from one paradigm to the other? It's hard for us to appreciate this now because we simply take it for granted. Everyone knows that the Earth is spinning and going around the sun. And if we can put ourselves back into that paradigm, okay? First of all, there's a very serious astronomical objection, right? The fact that you don't see any parallax. We were moving in this enormous orbit around the sun, 93 million miles on either side. Now, they didn't realize it was that big, but they knew it was big enough that you could see a parallax and you couldn't. Copernicus explained why you couldn't, because the stars were so far away, we just couldn't notice it. Sounds very self-serving. Sounds like a very convenient excuse. And again, if the stars are so far away, if they're so much further away than Saturn, what's the purpose of that? Is it just to make us crazy that we don't see the parallax? What's the purpose of all that empty space? Everything has to have a purpose. This is God's creation. He doesn't do things willy-nilly. He has a purpose for everything. And there would be no purpose for this vast distance of emptiness. So, does it make sense? So there's the astronomical observation. There's the problems of the moving Earth itself. What force could move the Earth? Come on. What force could move something so heavy, the heaviest thing in the universe? Why don't objects fly off the spinning Earth? When you have a wheel, potter's wheel, and you spin it, the stuff flies off the wheel. How can clouds and birds and everything keep up with the how can the moon keep up with the moving Earth, right? And when you drop something, why does it fall straight down to the center of the Earth? If it's spinning at tremendous speeds and going around the sun at even greater speeds, how come when I drop something, it falls right to my feet? If I'm moving, I dropped it, I let it go. Okay, no one's touching it. How does it have this motion that it can keep up with the moving Earth? How does that work? And finally, just from common sense, right? If the Earth is moving, why don't we have any sense that we're moving, right? When you're riding on a horse, when you're in a carriage, when you're walking, you have a sense that you're moving, but yet we have no sense at all that we are having these incredible motions that Copernicus and Kepler are asking us to believe. It just is very, very hard to understand how this can be the case. Okay? Guys, and if you want to appreciate this, move this to the dual reality, of electrons being both particles and waves. How do we understand that? It's as difficult for us. How do we understand the idea of entanglement? How do we understand these ideas? How do we understand Heisenberg's uncertainty principle, that no matter how hard you try, the better you know the position of a particle, the less you'll know about how it's moving. where it's moving and what speed it is. That you can't know both at the same time with unlimited accuracy. It's impossible theoretically to know that. The better you know where something is, the less you know where it's moving to. How can that be? Why must that be the case? Yeah, we're still in the middle of this paradigm revolution. And it's very hard for us to understand these things. As much as we try, and we watch the Nova shows, and we read the articles, and we read, it's very hard. Try to sympathize with people with these problems here. How can this be so? It just doesn't seem to make a lot of sense. This is what Galileo is up against. This is what he's going to try to overcome. And the heart of it, if you're looking for the heart of the scientific part of the scientific revolution, if you want to know the kernel, the nub, this is it. It's the law of inertia. That a body at rest will remain at rest, and a body moving at a constant speed in a straight line will continue to do so until acted upon by an unbalanced force. That is a statement from Newton. This is Newton's first law, and this is discovered by Galileo. And the picture here depicts a wonderful reading that I suggested I gave you 2 weeks ago from the dialogue, in which he has Simplicico go through motion on the inclined plane. If something is on an inclined plane and you let it go, what's it going to do? Well, it's going to just fall down. It'll go faster and faster. Well, what happens if you put something on rolling up an inclined plane? What will happen? Well, it'll go slow and slow until finally it'll stop. And finally, what happens if you put something on an inclined plane and let it go down and just let it go flat? Then what will happen? Well, suppose, well, I don't know. Let's see. It's flat. Says, and there's no friction. This is the perfectly idealized ball on a perfectly idealized surface where there's no resistance at all. Take away all resistance. I drop it from the inclined plane. It's now flat. It's not going to go up. Well, let's see. So it's not going to go up. So therefore, there's no reason for it to slow down. And it's now off the inclined plane. It's flat. So there's no reason for it to be going faster and faster. Well, I guess it would move forever. And he gets Simplicico to state the law of inertia. And this is right out of Plato. This is right out of the Socratic dialogues of having Socrates bring forth from someone, by questions and answer, a great revelation. Galileo is a master of this art form, just as Plato was. It's been said that Galileo was a beautiful writer of Italian prose, and that his prose at that time is among the most beautiful samples of writing in Italian that you will find in the Renaissance. So we have the law of inertia. Another view of the law of inertia, very much what we just said. You drop something from one height and it'll roll down, and without friction, it'll reach up. It'll keep going until it reaches that height again. Well, what happens as you lower and lower that other height? That it's got to go out further and further along before it gets back up to that height. Well, what happens as you lower it further and further and further down? It takes longer and longer and longer until you reach that height again. What happens if it's completely flat and you have no chance of reaching that height? It will roll. It'll roll forever. Okay. And this is fundamentally the law of inertia. The moving Earth. Take a look. The radius, the size of the Earth was well known. The size of the Earth was well known back to Eratosthenes in 2500 BC. I'm sorry, 250 BC. The size of the Earth was well known to the astronomers of this time. Had been known for 2,000 years. So at the equator, if you're moving around once a day, 24 hours, you're moving at 1,000 miles per hour. If you're at the latitude of Rome, which is a slightly smaller circle, you're moving at 770 miles an hour, spinning around in space once a day. That's the speed you would be going at to go make one revolution around. This is what Copernicus is asking us to believe, that you're moving around at 777 miles an hour. This is when the fastest thing on Earth that we know about is a thoroughbred. which is what, moving at 30, 40 miles an hour. This is 777 miles an hour. This is a speed that is beyond our experience. And then we're moving also around the sun. Okay. Now, their distance to the sun goes back to Aristarchus. There's still not a better distance to the sun, not in Galileo's time. So we're still using a number of about 6 million miles. That would be setting us around, giving the circumference of that kind of radius. We'd be going around the sun at 4,300 miles an hour. We're actually going around at 66,000 miles an hour, right, with 93 million miles from the sun. But again, you're asking me to believe I'm moving through space at 4,300 miles an hour. You see the difficulty here, how hard it is to accept this kind of thing. And I don't sense this at all, you know, and the clouds, which are just up in the sky, they're not attached to anything. They can keep up with this incredible speeding Earth. And so we'll end here. Let me give Galileo's argument, and then we'll quantify it a bit later. Question is, where will things land? This was a famous example that was given, okay? If I drop something from a tower, we know that it drops to the bottom of the tower. No problem at all. It's because the Earth is stationary. If the Earth were moving, right, then as the thing drops through the air, the tower is moving on the moving Earth, and it wouldn't drop in the bottom. It would fall someplace away from the tower, right? If I was on a ship and I climbed up the ship up to the mast, ship is moving along, I drop something from the mast of the ship, what's going to happen? According to Aristotle, it's going to drop like this. And this is discussed in the dialogue. It's going to drop like this. The thing will drop straight down, its natural motion, down to the center of the Earth. The ship will continue to move along while the thing is dropping down. This, of course, is an exaggeration. This is a very fast ship or a very, very tall mast. But the idea is here that it would fall beyond the bottom of the mast, because the ship continues to move while the object is moving down to the center of the Earth, which is not moving. Okay, this is what Aristotle's theory of motion would predict. Galileo says, "Did you ever do that?" And he says to Simplicio, "Did you ever do the experiment?" Well, no, I didn't. But I've read about it, you know, and I imagine those people who wrote about it, they must have done it. No, Galileo says they didn't do it either, because if you ever do it, what you'll see is that yes, it will fall to the bottom of the mast with no trouble. And in fact, when you look at the ship from a distance, you'll see, if you could, you know, hard to see because it happens so fast, that the ball will actually move in an arc, keeping up with the motion of the ship. So let me end with this animation, and I'll let you go. Just something to think about. So here is the violent motion that we're being asked to believe as we drop the ball, as it goes down through the tower. It's going to, if it's going to hit at the bottom of the tower, it must have had this trajectory, but this is a violent trajectory. What force is making it move in this kind of an arc if it's going to keep up with the tower? You know, in fact, what would happen is this. In the turning Earth, it would continue to move down to the center of the Earth, its natural motion. And so it would fall away from the bottom of the tower. But of course, this doesn't happen. That's because the Earth is not moving. And finally, the ship. What is Galileo talking about? And this is the last idea I want to leave you with. Galileo says, let us take our ship. Here's our ball from the mast. And as the ship goes underneath the bridge, I'm going to drop a ball that's stationary on the bridge, drop it at the same height as the ball from the mast. And what's going to happen? Here we drop the ball straight down, it's not moving, and I drop the ball from the moving mast. What happens? Well, we know the ball falls down according to law of free fall, whatever that is. And this ball here, this ball will continue to drop. It will drop just like the ball of free fall. But at the same time that it continues to drop, having the same height as the ball that simply dropped, it'll continue to move along with the ship. It will not slow down because there's no force to make it slow down. So it will have a combination of two motions. It'll have the motion of free fall and it'll have the motion of inertia. And with those two motions together, it will create this arc. And Galileo is going to prove, and one of the highlights of our whole course, of our whole 8 classes, that we will prove next week, that this curve here is a parabola. Okay, guys, so that's it for today. Any questions or comments before we go?
Peter, just tying that last bit to the whole notion of common sense, it seems like sailors at that time could have been playing catch on a ship and have noticed the same thing. Gee, why are we able to play catch if the ball is not moving along with us?
Exactly, Mike. And that argument was made. And again, people, have an interesting blindness about what they believe in terms of an ideology and what is real. And they can hold these two things separately without much trouble. So yes, people did understand that. People did understand the idea of relative motion, that you could be moving so slowly on a very quiet water that you wouldn't know you were moving. People do have these experiences, but yet these were the arguments that the philosophers made. This is what had to be combated. And your example, and just one with your example of playing catch, I have the very famous reading from the dialogue that I want to read next week. It's in the Word document that I sent in Tuesday's email. If you want to read that, Mike, one of the things he does in his thought experiment is he has two people playing catch down the bottom of the cabin of the boat as it moves along. So take a look at that reading. Anything
Thank you,
else?
Peter.
Okay, guys, have a good week. We'll see you we'll finish up Galileo next week, and next week will be probably our most important lecture. We really will get to the heart of the scientific revolution. Okay, guys, see you then.
Thank you. Thank
All
you.
righty.